Okay, welcome to the last hottest seminar of the season. Today we're very pleased to have Ulrik Buchholtz from TU Darmstadt, who will be telling us about co-Cartesian families in simplicial type theory. Please go ahead.
Thanks so much, and thanks for having me. Thanks everyone for coming. Yes, as you can see on the slides, this is joint work with Jonathan Weinberger here at Darmstadt, and we've been working on this for a while, and I'm looking forward to this opportunity to give you an update on our progress. We just put out a draft manuscript with a bunch of the stuff that I'm talking about today. You can get these slides afterwards and then see it. Otherwise, someone can post them in the chat if you want to click on them and read along. Okay, so here's the menu. The setting is Riehl and Shulman's simplicial type theory. So I'll talk a bit about how I view that project. I give an introduction. And then the second part will be about Cartesian and co-Cartesian families. And then I will prove a Yoneda lemma for these. And then I will talk about what the future might bring after that. Let me just test that this works. Yeah, so I can write here, feel free to interrupt if you have a question. And also if someone can watch the chat, and if something happens in the chat that I should know about, let me know. All right, so a bit of motivation. Why are we interested in simplicial type theory? So the past years, the last year in particular, has seen a lot of progress on the major open problems in homotopy type theory, but one of them is proving very stubborn. And that's the problem of how to define the type of infinity one categories in hot and then develop the theory of them. One can reduce that a bit to the problem of defining the type of semi-simplicial types. And it's annoyingly difficult. On the other hand, it seems just as difficult to prove that it's impossible. So there's sort of two ways this can go. Maybe there'll be some very complicated construction. And then it might still be nice to have a domain-specific language, a type theory or something like that, that we could use to reason synthetically with infinity one categories and then compile this language into hot and then apply it to some higher categories you encounter in nature. Or maybe it turns out that there's an impossibility proof and we have to extend type theory, and maybe we go to two-level type theory, and then it'll still be nice to have this synthetic type theory for higher category theory that we can use. Okay, so that's how I see this. So what is such a domain-specific language? Well, there's this very nice article by Emily Riehl and Mike Shulman, A Type Theory for Synthetic Infinity Categories, which is inspired by RESC model structure on simplicial spaces. And in there, you can carve out infinity one categories. So I'll talk a bit about how I see that. So for the whole project of working synthetically with higher categories or doing directed type theory, there's a bunch of related work. And I mentioned some of it here by reference to some authors. And I'm sure I left someone out, and I'm sorry about that. If you feel I left you out, just please forgive me. But there is some work on two-dimensional directed type theory by Bob Harper and Dan Licata. There's work by Michael Warren on directed type theory. A nice thesis by Andreas Nutz on directed type theory as well. Dan Licata and Matt Weaver. Matt Weaver spoke a year ago, more or less exactly, at Here at Hottest about their approach to more or less this version of simplicial type theory, but done in a more computer science fashion, where you want to have a constructive model and do some things. Work by Evan Cavallo, Emily Riehl, and Christian Sattler on directed univariance in this setting. I'm also going to just point to this work on infinity cosmoses, because we are inspired by that, even though it's not type theory. it's still an approach to synthetic reasoning about higher category theory, so I'm going to mention it here. Denis Charles spoke also a year ago at Hottest about something related. Page North is working on directed type theory, and as I said, I'm sure I leave something up. So lots of activity around this area. All right, so now some motivation for studying Cartesian and co-Cartesian families. So in the paper by Mike and Emily, they study and define covariant and contravariant families that are representations of co-presheaves or presheaves over a base category. So one might think, well, you have a synthetic theory of categories. Why not just have this universe of spaces here, spaces in the sense of infinity groupoids? Well, that's hard to get, and if you want to get it, you somehow need to start with the covariant families. So better study those first. And so here we want to do a parallel study of co-Cartesian and Cartesian families, which represent families of categories that are either functorial or covariantly functorial or contravariantly functorial in a base category. And these are useful for all sorts of things. So for instance, there are many examples where you have a family of categories parameterized by some objects. Take the category of modules over a ring parameterized by the ring. This is both covariant and contravariant in various ways. Or the category of vector bundles on a manifold. So those are things we would like to study in mathematics and have a good theory of. Another use is that you can use co-Cartesian families to define other categorical notions. For instance, a symmetric monoidal infinity category is a co-Cartesian family over the base category of finite pointed sets. And parallel to the use of covariant families to define the universe of spaces as a category, you can use co-Cartesian families to define this universe cat of categories and functors. So the infinity one category of infinity one categories. Okay, I'll return to this at the end. Okay, so now let's start with point one, which is a brief recap and maybe new look on simplicial type theory. So I'm gonna, in this talk, do it slightly differently than it's done in the paper by Mike and Emily. I'm gonna work in the simplest possible simplicial type theory. We simply postulate that we have a set with an ordering, 2 points, and a proof that this is a strict interval. So a strict interval is a totally ordered set with distinct top and bottom elements. So we draw it something like this, and I'm going to call it both 2, but I'm also going to call it delta 1. And indeed, in one-topos theory, the one-topos of simplicial sets is the classifying one-topos for these guys. And the infinity one-topos of simplicial spaces is the classifying infinity one-topos for these guys. So somehow, by postulating these data, we are placing ourselves in a constructive version of simplicial objects in any infinity one-topos. So in particular, totality, which says, let's see, total, let's put that here, either x is less than or equal to y, or y is less than or equal to x. That's the totality axiom. This, of course, is the join of these two propositions. So if you think of this as a subtype of the square, it's the whole square, but it's also going to be a push out because it's a join. So you have the subset of square where x is less than or equal to y. That's the same as a 2 simplex. And here you have the subset where y is less than or equal to x. That's another 2 simplex, the lower one and the upper one. And then here you have the subset where x is equal to y. Well, that's just the delta 1. And then this is a push out. So you can define maps out of the square by giving the value on the upper part and the lower part, as long as your constructions give you the same result on the diagonal. Okay, so for instance, you can use this to define the connections from the square back to the interval. Okay. So what else can we do in this setting? We can define all the simplices, even uniformly. The boundaries of the simplices. So the simplex here, we're going to sort of the bottom ordered part where the last coordinate is less than or equal to the second to last is less than or equal to, and so on. The first coordinate is less than or equal to 1. So you have n+1 inequalities here. And the boundary is the part where one of these is an equals. And the horn is one of these, where one of these, except the kth one, is an equals. So these are easily defined along with the embeddings. Given any type, we can define the type of arrows. So we draw usually a type like usual. We draw it as a blob, and you have maybe 2 points. And then you say you want to map from this directed interval, and then, well, you can add a path from the beginning and end to the beginning and the end point. I find it's not so bad to work with this, even though in the Riehl Shulman paper, they introduced some extensions to the type theory using shapes and topes, for which you can make this more strict. But here I'm just going to think about it in the basic type theory way. This is a special case of an extension type, which is something that has a strict structure as a primitive type former in the Riehl Shulman paper, but you could also just define it for any map and a type family. So let's maybe draw it like this. You have some type psi, and you have a map. Doesn't even have to be an embedding, but usually we think of it as an embedding. And here's phi. You have some type family living over psi. It's the total thing of A with the projection. And you have a section A on this part, and then you have the extension type is the sections F that once you compose them with I become equal to A. Okay. Now the next thing we need is dependent arrows, or arrows lying over arrows. So just like for the identity type, it's useful to think about paths and paths over paths. For directed paths, we do the same thing. So we draw one of our usual pictures of a base type and a type family lying over it. It's P. And we say, let's say we have a directed arrow here in the base. And we have a point in the fiber here and a point in the fiber here. Then the type of arrows lying over U, F, we can give as an extension type relative to the, so we have the 2 endpoints sitting inside the directed interval. U is this map here to B. This is delta 1. This is 1 plus 1. And E and E prime are these points up in the total space, agreeing with the endpoints of the directed path U. And then an F is an extension like this. So it's also a lift in this square. Okay.
Can I ask something?
Yes.
So do you view the extension types or the strict equality as primitives? I mean, in particular on the previous. Okay, sorry. Then can you go back to that slide? So there in this line where you define the morphisms, wouldn't you want these equalities U0 equals B to be strict?
No, because that would require some extension to type theory, which I don't want to have for here. I want to think about just ordinary type theory. So these are the usual identity types.
Okay, I see. So that makes it really different from what Mike and Emily have suggested, I think.
Not much, because if you take their theory, you can still prove an equivalence here. So let me, here we get an equivalence if you promote their shapes to be types, so you could make sense of it.
Mm-hmm.
So it's not really different. It's they give you a little bit of extra strictness, but it's not something that is fundamentally different. You can still do everything just in this version which is just basic type theory extended with a strict interval.
Right. I mean, this seems similar to the translation between fibrations and type families, right? Where one notion is a bit stricter.
That's right.
Yeah, so then when you go to higher levels and have to formulate more coherences, it becomes very tedious to do this in this weak setting, no?
That's a good question. So I haven't formalized any of this. I know that Dan Licata formalized a bit of simplicial type theory in ACTA with rewrites. And yes, I can see it both ways. I think if you abstract a bit, you might be able to formalize things just fine in the setting I'm suggesting here, where you just have type theory extended with a strict interval. You have to prove some results that let you go between things. But I mean, if you're proving something a very general picture, you can start by doing a bunch of path inductions, and then you get rid of you get rid of a lot, and then it's simpler. I don't really know until someone formalizes it both ways. I don't know which is in the end simpler.
Okay, thank you. Yeah, makes sense.
Yeah. Okay, so this was arrows, independent arrows. Okay, so with this, we can define the Siegel types. These are the types that are local with respect to the horn inclusion. So the horn is the composable arrows, either as a subtype of the square, but it's also a push out of two directed arrows along an endpoint. So let's see, I guess this is, take the one endpoint of one of them and the 0 endpoint of the other, and you glue them together, you get this horn, and this sits inside the two simplex, which is filled. Okay, so if a type is local with respect to this means that whenever you have two composable arrows, there's a unique composite together with a filler. Okay, so the Siegel types form a reflective subuniverse. And they are the model of pre-infinity one categories, or if you like different terminology, just the categories, or maybe you want to think of them as the flagged infinity one categories, because there's some extra structure in the objects that is not yet characterized. But the important part is that associativity follows. And again, this is related to the previous question about, how would things look in this if you actually formalize this? I think it should be possible to derive the uniformly in the natural numbers, the locality with respect to all spine inclusions. But I haven't thought much about this, but I think it should be possible. It's something you can do for a meta natural number for sure. So one will have to think about whether it could be uniformized. But often you don't really need it. You'd need to know that you're thinking about the right objects. You need to know that this is true. And in practice, you only need it for small n. So n equals to 3 gives you associativity, and 4 gives you coherence of associativity, and so on. Okay. Now, how do we define isomorphism? Now we talked about morphisms. So if let's just say we're working in a Siegel type, then an arrow is an isomorphism if this type, which happens to be a proposition, is inhabited. So what is this? So you have B as a blob again, and you have an arrow from A to B, F. And this says that there are two other arrows. So an arrow from B to A, G, and an arrow from, another arrow from B to A, H. And then this should be an identity, reflexivity. And this should be reflexivity. And then you should be able to fill this. I'm implicitly using that it's a Siegel type to make sense of these composites. So I guess I did do it the other, but maybe I need to move it the other way around, but it's okay. So you can prove easily that this is equivalent to the mapping type out of a certain type E, which is the picture that is here. So it's you glue two simplices together along a common edge, and then you collapse this edge to an identity and this edge to an identity. And this co-limit we can define using pushouts, for instance, and then you can define this type. Now the rest types are the Siegel types that are E null. That is, they think of E as a contractible object. So the map that sends a B to the constant function from E to B is an equivalence. So any such isomorphism must come from an identity. So this is equivalent to the statement that the map from identity types to directed paths is a fiberwise equivalence. It's also equivalent to require that B be local with respect to one of the two endpoints inclusions of this walking invertible map. So the rest types are the models for the internal infinity one categories, or the univalent pre-categories, or the flag categories where you can contract away the flag. And then we also have that a type is discrete if it's null with respect to this to the interval. So these discrete types are risks, and they model the infinity equipoise. So this is the basic setup. Okay, I'm still just doing a recap. So the Yoneda lemma that is in Riehl and Shulman's paper is the following. So first we define what it is to be a covariant family. This is to be right orthogonal to the left endpoint inclusion to the interval. If you're contravariant, that means that you're right orthogonal to the right endpoint inclusion. So let me see if I can fit a picture of this. Drawing the standard picture of a type family. Then, so I have an arrow in the base, and I have an element over the left endpoint. Then there's a unique lift. That's a covariant family. So yeah, you have a unique way of going forwards. Now, the Yoneda lemma in this form says that if you have a Siegel type with a point and you have a covariant, oh, that should be a B, sorry about that. You have a covariant family, then evaluation at the identity gives an equivalence between these natural transformations. So you can think of this as transformations from B blank to P. You can evaluate such a natural transformation at the identity, gets an element of P of B, and this is an equivalence. Now, there's also a dependent version of this. Here you have a family over the total space of Hamming out of B. So this is the slice B under B over B. This is a covariant family. Then you get an equivalence like this, again by evaluation at B. And this says that the inverse map here, you can think of it as a directed version of path induction, or directed path induction. So if you have a motive that is covariant in a point under B, then to inhabit it is the same as to just give an element at the reflexivity path. Now here's a small observation. This is not in Riehl Shulman, but I think it's kind of cute. There's an analog in the directed setting of the fundamental theorem of identity types. So take a Siegel type with a point and a covariant family and an element in the fiber over the chosen base point. Then we just have this fiberwise map, which is given by covariance. So, and the element B. So you take an arrow, let's make a picture here. So you have B, you have P, you have your beginning point B, and then you look at arrows out of B to some X, and you fix the element of the fiber D, then you can always, using covariance, get a map from any U to this element here. And then the statement is this map is a fiber-wise equivalence, so it characterizes the Hom type if and only if this point in the total space, so the pair of B and D, is initial in this total type. So let me sketch the proof of that. So it's a kind of directed version of the encode decode methods. You want to know the Hom types in a Siegel type. You construct, it must be a covariant family. So you construct a covariant family with a notion of reflexivity. And then you get this map by covariance. And then you just prove that this element is an initial object in the total category. And then you know that your family is equivalent to the Hom types. All right. So if this is a fiber-wise equivalence, then this is pretty clear because the pair B and the identity at B, this is initial in the sigma type, sigma X and B, B arrow X, the Hom type. Okay, so if you have a fiber-wise equivalence, then you get that. In the other direction, let's look at a fiber of this map. Let's call this map phi. Let's call it, yeah, okay, let's call it phi. So the fiber at phi of X, add an element E. So let's say I have an element E over here. What is that? Well, it is the sum of an F. Let's call it a U from B to X, B, together with a path, an undirected path from the functorial action of U on D to E. Okay. Now, but in a covariant family, to give a path here is the same as to give an arrow, a dependent arrow from D to E lying over U. So this is the same as sigma type over U from B to X, and an arrow from D dependently over U to E. Now, by the yoga of taking things apart and putting them back together, an arrow in a sigma type is such a sigma type of arrow. So this is the same as an arrow from the pair BD in, so it's sigma BP to XE. But this is an initial object, so this arrow type is contractible. So this fiber is contractible, so this phi X is an equivalence. Okay. So we haven't found much use for this, but I expect it to be quite useful later on when we get to proving univalence for universal families, which is not in this graph, but it's a future work, which I'll get to at the end. Okay, now let me move on. This was the first part. Now we're coming to the Cartesian and Co-Cartesian families. And again, please interrupt if there's a question. Okay, it's useful to have an extra notion, named the notion of an inner and an iso-inner family. We say that a map is inner if it's right orthogonal to the Horn inclusion. And we note that if the base is Siegel, then the total type is Siegel if and only if the map is inner. And we say that pi is iso-inner if it's an additional E null. And so this means that if you have a resc type and an iso-inner family, then the total type is resc. And if you just care about categories that is resc types, then everything is iso-inner. mainly a technical device. You can forget about it now. Okay, what is a co-Cartesian arrow? That's a critical component of defining the co-Cartesian families. Just a note, I'm going to do most things mostly for the covariant and co-Cartesian case, but you can swap all the arrows and you get the contravariant and the Cartesian case as well. Everything is dual. All right, so here's the picture. Now I need a little bit more room. So I'm not, I'll draw the base. I need a bit of two-dimensionality. So it's going to be a blob. And then I can't promise you. So now there's some, the fibers are not going to be exactly where you might hope, but I'll try to draw things vertical as possible. So here's P, and of course I may also think of, this is the total type of the family. Okay, so what are we defining? We are having an arrow F in the total type lying over some arrow in the base. Okay, now we want to say, what does it mean for F to be a co-Cartesian arrow? And I'm going to decorate them with 3 little bars. That's just a piece of notation. Let's see. Okay, so what is the condition? We are given a 2 simplex extending U in the base. So this looks something like this. And then we are given an arrow over the diagonal in the square. So that's a long edge of the 2 simplex. So that's something over here. Let's call this was called sigma. And this is H. And then something has to be contractible, namely the ways of extending this, the extension of this to a 2 simplex here with a filler here. That has to be contractible. Okay, that's a co-Cartesian arrow. And we say that F is a co-Cartesian lift, or that should be of U, starting at E, if you have a lift of U and it is co-Cartesian. So here's a lemma. If your base type is RESC and the family is iso-inner, then P co-Cartesian lifts are unique. So the type of them is a proposition. Won't bother you with the argument. What I will spend a little time on is the following cancellation property. So here we have a map of RESC types, and again, I'm going to sketch it a little bit. We have B. I'm moving rather freely between the maps in the of types and families of types that are going between the map and its fibers and the fibers in the total space. I hope that doesn't bother anyone. So here now it's called E, and we have a map pi here. So we have composable arrows in E, F, and G, and these are RESC types, so they're categories, so you might as well put in the composite. So here's F, here's G, and here's G composed with F, and here's a filler. And of course, that lies over a 2 simplex in the base. Now, let's assume that F is co-Cartesian. Then the statement is that G is co-Cartesian if and only if the composite is. So the way from if G is co-Cartesian, then the composite is, that is pretty easy. And I'll leave that as an exercise for you. And I'll just sketch the other direction because I'm going to appeal to it in a few minutes. So the other direction, we are supposed to show that, so let's say we assume that the composite is co-Cartesian, and I want to prove that G is co-Cartesian. So I take a 2 simplex extending things here along with a map on the long edge lying over the long edge here. Then I can compose, so let's call this something H. I can compose H with F to get something here. And then the composite is co-Cartesian. So I do get also over this, I can compose these 2 simplices. So I get a lift here. And then we we can prove that this is the unique thing that makes everything work. So that's sort of why you have this right cancellation property as well, but you don't have the left cancellation property. Okay. What is now a co-Cartesian family? We say that an isoinner family is co-Cartesian, basis resc, if these co-Cartesian lifts always exist. Remember that the type of them is a proposition, so this is a proposition that these propositions are always true. And this implements functoriality. If you have an arrow in the base, and you want to have a functorial map, then, well, you take an endpoint, you want to have a map over to this fiber. Well, you take the co-Cartesian lift and take its endpoint, and that implements the functorial action. And if you have a composite, then this works nicely with composition, uniqueness of co-Cartesian arrows. Okay. And of course, you're welcome to dualize things and get Cartesian families and the contrariant functorial action. Okay. Here's one thing. We prove a lot of things about co-Cartesian families in the paper. Here's one of the things we prove. A map of resc types is co-Cartesian, represents a co-Cartesian family of the fibers, if and only if we have a Laury adjunction, where I'm just going to remind you, a Laury adjunction is a left adjoint right inverse to the gap map in this pullback Hom for the left endpoint inclusion. So you can, this pullback corner, and again in the picture, you have E and B, and this pullback represents a directed path in the base together with a chosen lift of the left endpoint. And this left adjoint to the map from that takes an arrow in the total space and just returns just this information, the left endpoint and what it's lying over. This left adjoint will be the co-Cartesian lifts. This is L of UE. Okay. Now, using a characterization like this, you get a lot of results following from it. You get closure under dependent product. So you get exponentiation, you get composition, closure under pullback. We can also prove that the domain map is always Cartesian with Cartesian lifts given by composition, and it's co-Cartesian if B has push out, and the codomain map is co-Cartesian, and it's Cartesian if B has pullbacks. So this kind of thing you expect to happen, this all happens. Okay. That's all I'm going to say today because we're going to get to the two Yoneda lemma. Let's see, time. Okay. So here's our dependent version of a Yoneda lemma for co-Cartesian families. Start with a rest type with an initial object, and let P be a co-Cartesian family. Then evaluation at B induces an equivalence from the co-Cartesian sections of P to the fiber at the initial vertex. So here B has an initial. So I'm going to draw it all the way to the left and think of B is sort of directed out from little b. And then I have a co-Cartesian family. And this means that if I have any lift over the initial point, well, then I can, for any point, I always have the unique arrow given by initiality. For some reason, we call this empty set X. And because we decided not to call the initial object the empty set, so to remind you that it has something to do with an initiality, we call the unique arrow the empty set at X. But never mind. So you have these co-Cartesian lifts that give you a picture of B starting at any D in the fiber. And so you can always recover a Co-Cartesian section, which is one that maps arrows in the base to Co-Cartesian arrows from its value at the initial object. Okay. And then from that, you can derive a corollary that is a non-dependent version, where you just take any element in a rest type and have a Co-Cartesian family over B, and you get that evaluation at the identity at B gives an equivalence here, where you look at Co-Cartesian sections of Q composed with the endpoint. So you have the endpoint map partial 1 from the slice to B. So this represents the families here, remember, are Hom B blank. That's the corresponding family. That's corresponding family. And you can compose this with Q. And this is a Co-Cartesian family over now the slice. And here you have the identity as an initial object. And then you can appeal to the dependent version and you recover this. And let me just also note that this type of Co-Cartesian sections of the composite is the same as the Co-Cartesian natural transformations. So here you have this B over B sitting over B, and you have this other family Q bar for the total type, and then you have the type of Co-Cartesian functors. So object-wise functors here that send Co-Cartesian arrows to Co-Cartesian arrows, but this is a covariant family. So every arrow is Co-Cartesian. So this means that that's the same thing as requiring a Co-Cartesian section, because we require for every arrow in the slice that you get a Co-Cartesian arrow in Q. That's why it's equivalent. Are you with me? Then I'm going to prove this version. Okay, so I put the beginning on the slide and then I'm going to draw the rest of it. So I'm actually not going to prove that the Yoneda map is left adjoint right inverse, but we do that in the paper. So what are we going to do here? So we have this type of Co-Cartesian sections. Co-Cart EP. This is a subtype of all the sections. And we have the evaluation map to the fiber at the initial object. And we can also evaluate on all sections can be evaluated at B. And now the claim is, well, that's not what I'm going to prove, but I'm going to construct a map here that's going to be a section of the evaluation of B, and I'm going to call that Y. And then I will show that it gives an inverse here. Whoops. So it restricts, it maps, it takes values in Co-Cartesian sections. Okay, so here's the picture of what Y is doing, echoing the picture on the previous slide. Okay, so here's B, here's P. And again, we're assuming that little b is an initial object. And we're going to define y of d. So y of d, where d is an element of p of little b. This is supposed to be, first of all, a section. So here's D. So what should be its value at an X? Well, we look at the unique arrow from the initial object to X. We take the Co-Cartesian lift, and then we get the functorial action of P along the initial, the unique arrow from the initial object. And then we lift D. So this object is our Yoneda D at X. This lives in P of X. Okay, so this is Yoneda D of X. I'm going to write the same thing down. Take the functorial action in P from this arrow starting at D and then evaluate at 1. I don't know if I called, maybe I called this the endpoint. Okay, so far so good. Now let's see that this actually factors through this subobject of the co-Cartesian arrows. And here is where it's useful to think of these mediating co-Cartesian arrows as forming a natural transformation. So what could they be a natural transformation of functors? Because this is not a section, but we're not thinking about sections. We can think of the constant map at D as just a functor from B to E, not a section. So E is, again, the total type here. So E is sigma BP. So this is the functor that's constantly this pair, maybe B and D. And then we have Yoneda being a section also gives a map to the total space, of course. And now we have this natural transformation chi from constant D to Yoneda D for all D. So what is a naturality square? And we want to prove that, so let's say let U from X to X prime in B be given. And I want to show that Yoneda at D takes this to a co-Cartesian error. But we have the naturality square given by this construction chi. So this means that we have, so add U, it gets this, so D is constant. So then nothing happens here. And then we have this co-Cartesian arrow chi. I'm not naming the argument for some reason. And then it goes to Yoneda dx and to Yoneda dx prime. And this is the action on the directed path U of Yoneda d. And here's a co-Cartesian arrow. But now we have a composite that's co-Cartesian, and the first leg of the composition is co-Cartesian. This means that therefore, let me make this in another color. This is co-Cartesian as we wanted. So we have a map Y that takes values in co-Cartesian sections. And it's also the case that if you plug in, if you evaluate at B again, then you get D back. So it is a right inverse. It's a section of the evaluation. All right, let's continue the proof. So now we have, let's recap. So we have the evaluation at B. So I'm going to call this type T, the type of co-Cartesian sections of P. And this goes to P of B. And I have this Y, which and evaluation at B composed with Y is the identity on the type P of B. Okay. And now I want to show the other composite. So let's look at Y composed with evaluation at B. And I want to show that this is equal to the identity on T. Okay, what is the type of these identities? Well, by function extensionality, it's the same as for saying for every sigma in T, so for every co-Cartesian section, and then there's some round trip. So for every X in B, I need an isomorphism in P of X from Yoneda at sigma. See, I evaluate at B, so it must be sigma B, sigma D. We fix. Yes, evaluation at B. Yes, take this section evaluated at B. Take Yoneda of that point. Maybe I remember to draw my picture again, then I can orient myself a bit better. So we have a co-Cartesian section sigma. Here's our initial object B. Here's sigma at B. Okay. And I want an isomorphism in P of X from Yoneda from sigma B applied to X iso, so that is a path, to sigma of X, which is the identity evaluation. So sigma evaluated X. That's what I want. So let's say I'm going to call the element I'm going to construct, I'm going to call it epsilon sigma X, and it has to be an isomorphism in this fiber. This has to be my epsilon sigma X. Now, how am I going to go to get that? Well, it's not so hard. I have this co-Cartesian, this other co-Cartesian left here, this chi natural transformation from before. So of course there's a factorization, and it's, well, there's several ways of saying it. It's, since co-Cartesian lifts are unique, of course you have this isomorphism here. You can also say, well, lift this one here, and then by cancellation, this is a co-Cartesian error over the identity. So it's a vertical co-Cartesian error, hence it's an isomorphism. So it's, that's the proof. I didn't write everything down. Maybe for posterity, I will write epsilon sigma X is the lift. That's the filler. From chi to sigma applied to this, to the unique map here, the unique arrow b to x, and this is a vertical co-Cartesian arrow, therefore iso, therefore identity. Okay, and that's the proof. And now let's talk about where we go from here. So the outlook, I see it matches pretty well with the time. So this is the last slide. Where do we go from here? Well, I think we have done a lot what we can do just in the basic simplicial type theory, which I kind of like this setting, and I do hope someone, maybe if I have the chance, I'll formalize some of it and see how easy it actually is to work with. The next thing we would like to do is to bring in cohesion, because simplicial spaces are cohesive over all spaces, and that is indeed constructively true. So no matter what the base topos is, you always have, so if the base infinity topos is E, and you have simplicial objects here, you have a string of adjoints, you have a cohesive setting, and you can talk about the discrete and co-discrete and so on. This seems to be necessary to give a good theory of Condorcet functors, and we hope to have a descent theorem for these using the cohesive type theory. And the next level up would be to define the universes using a cubical exo layer, where you, in the cubical exo layer here, delta 1 is tiny. And that's what you need to define these universes. And then we hope we can prove that they're univalent without adding new constructions, just using higher inductive types. And that's where the directed encode decode lemma would come in. But that still doesn't quite give us like the unique, the naive version of the Yoneda lemmas, which talk about this, you know, pre-sheaves as maps from B up to spaces to this universe. And you want to talk about the functoriality also in the other variables. So you need, basically you need to have Hom, something like from B up to B to a universe. And then you want to say, okay, this has some kind of mixed variance, has to do with the twisted arrow. So you need some extra modal structure to get a good handle on that. And okay, so I started out by saying that we wanted to use this as a DSL, and I want to end by maybe making a question to you. Could you conceive of using this, something like this, as a foundational system if we add enough structure and axioms? I mean, ideally, you would want to be able to bootstrap, so you can say that that the simplicial objects, which are the basic, so the synthetic objects, really can be built up by somehow more hands-on operations from homotopy types and diagrams. So it eventually comes back to, the question comes back to biting its tail. Could we look at these, could we look at the diagram somehow as simplicial diagrams in the universe of spaces, so infinity group boards, or the internal version? And that would be somehow, then you would have enough expressive power to, for instance, prove that the one categories, so the one truncated categories, are the same as the analytically defined one categories, where you take discrete, that is directionally discrete type of objects with Hom sets and prove the category structure, and then you want to glue that together to get a simplicial object. That would obviously require some structure on this type theory. Anyway, that's maybe some food for thought, and I will stop here, and thank you for your attention.
Okay, thanks very much, Ulrik. We will do our usual silent visual applause. And I open the floor to any questions. Feel free to unmute yourself if you have a question.
Maybe a suggestion as much as a question or comment.
So we're having some trouble with Thomas Streicher's microphone, I think. Maybe Emily, go ahead, and we can then try Thomas after. Oh, you're muted, Emily.
Sorry. So this is great. It's a lovely presentation as well. And I'm very happy to see all of these results in this setting. So one of the things that you proved is that the co-Cartesian families can be sort of characterized by, or define in any case, a left adjoint right inverse to this gap map, or whatever you want to call it. And one thing that Dom and I realized recently is that there is a similar characterization of co-Cartesian arrows, or sort of families of co-Cartesian arrows. We express it in slightly different language. So another way to say that you have a left adjoint right inverse is to say that some triangle inhabited by an identity, I think it's the unit in this case, is an absolute left lifting diagram, which is some weird two-categorical thing, but you can express that as an equivalence between comma objects, so in a way that would be more natural in this sort of setting. And a feature of these absolute left lifting diagrams is that they're stable under restriction, and that's essentially the form of the characterization for Cartesian arrows. And we've found that kind of nice to work with. And in particular, it gives another route to proving that the composition and cancellation result for co-Cartesian arrows. So I just thought I would mention that.
Yeah.
It seems conceptually interesting to me. It's I don't know. Now I think of this as kind of some generalized elements version of co-Cartesian families, and it might be particularly amenable to this perspective.
Yeah, that's great. Maybe you can get in touch by email. I would love to have that spelled out, because I don't really have, maybe Jonathan can take notes as well, but it'll be great to get in touch on that. We do have another characterization of co-Cartesian arrows in terms of a criterion by, I think, the studio under Riehl, that also has a flavor like this, but I don't think it's quite as too categorical as what you're talking about. So I think it's different.
Well, it might end up being the same because there's sort of a relative adjunction way to say this absolute lifting diagram stuff. And
yeah,
I mean, I wouldn't be surprised if Riehl has figured this all out already. So.
All right, yeah, that happens a lot. Thanks.
Okay, Thomas, should we try again?
Yes. So my impression now is, well, the background is if you look to the literature and you look at Lurie or Szysinski, when they speak about vibrations, they're speaking about grothendieck vibrations, meaning you'd really take equality of objects as usual, as it appears to me in what we've seen today. You're rather looking for the more liberal notion of straight vibrations, is that right?
That's right. Although I think of it as more restrictive because that has to work. I mean, it only works for the actual categories. Somehow the grothendieck vibrations in this setting would, as I understand, would be at the level of Siegel types or categories together with an object flag, and you have some extra structure on the object flags, and that can be helpful, but it also is a complication. I haven't really thought about what extra structure one would need in the case where you don't have the rest condition, but you have these extra object data.
One. I mean, if you do ordinary fibered categories, then, well, maybe just out of a conservative attitude, one considers grothendieck vibrations, for example, when considering B fibered over itself. And now, well, what are straight vibrations? It's grothendieck vibrations closing up on the categorical equivalence.
Yeah, that's now what we would have here, yeah.
Yeah, if you would work on this level, it would mess up things in a horrible way because, I mean, this jumping back and forth between, so to speak, indexed view and fibered view is intrinsic, at least for guiding intuitions. So would you say that in this case, this difficulty is taken over or hidden or made sort of harmless by the machinery of type theory?
Maybe there are two ways to look at this. One way is that if you're just interested in categories and not the object flags, then I think type theory is great for this because it somehow, you can do everything you need at the level of categories. I don't know enough to say whether you might be interested in some pre-categories, so categories where the object flag really gives you some extra information and you want to have some notion of vibration that takes that into account. But I think that should still be possible by looking at Siegel types. You just have to be careful because some types are no longer propositions because you might get there are many different, I mean, isomorphisms are not identities, structure there. I think that's
okay. May I translate this into my simple-minded world? I mean, if you're working with straight vibrations instead of grothendieck vibrations, you're of course not working in a univalent world. Their isomorphism is not equality. So I take your reply as saying that these problems, why you wouldn't do it in a setting without univalence, though this problem is overcome since you heavily exploit having univalence.
Yeah, I think for most of, okay.
I'm a little bit confused. I would have thought that we get that what you're defining is a grothendieck vibration because you're talking about co-Cartesianness of a type family. And so the codomain of your co-Cartesian lift does live strictly over the codomain of the morphism downstairs because it's in the fiber.
I know, but I mean, but at some point, I mean, that's what I remember Jonathan told me most of the time. Therefore, I was very surprised to hear today that equality as opposed to the original Riehl Shulman setting is not interpreted in the strict way, but in this more liberal way of equality as isomorphism, right? So there is a difference. I mean, because there is this, this allusion to two-level type theory, which essentially means that because of the outer level, you can speak about equality of objects. Yeah, that would be an approach to the whole thing more following the way done by Sisinski and who was also in Lurie. So I got, so my ears, so I got attentive when Ulrik mentioned that he's working now with equality as isomorphism, and therefore, yeah, I'm asking how much it changes. So I mean, the impression you see, the point is you have given the bare definitions and shown the most basic theorems. It would be most interesting to see what happens if you really use this framework for doing things vibrations were invented for. I mean, well, they were Grothendieck invented it for certain purposes coming from algebraic geometry. I am used to vibrations for doing category theory over a base topos. And there things only work, at least to the extent we know, when you're working with Grothendieck vibrations where equality of objects plays an intrinsic role. So it could well be, yeah, well, I mean, one has to say, if you take some text on fibered categories, not so many available, but there are. Johnston has it, my notes, whatever, and tries to develop the theory there in this setting, and then would be very interesting when proving the basic theorems, whether you run into problems or not. So, are there experiences? I mean, I've seen some on the chat. I've seen that Jonas Frey tried it, and he said he has run into problems, but also said might have been due to his not so much acquainted with the system he was using. So I mean, yeah. So I mean, the question is, when one starts using this framework and try to do the things one usually does with vibrations, would be most interesting how easy it is to survive without equality of objects you're usually using unconsciously, right?
So let's see if there's any other comments or questions about this. Or can you maybe try to clarify something related to the last point on your slide, which is, and you mentioned hoping to try to formalize this. So what exactly would you have to do in a proof assistant to try to formalize this? How much are you proposing to be changing type theory? It wasn't entirely clear.
Okay, so what I was proposing to formalize was just the main parts of the talk where you need very little and you just postulate a strict interval and go from there. And you don't have to change anything to a proof assistant to work with that. You don't need any extra rewrite rules or context machinery, nothing like that. You just go to town. Now that's not related to the last point on the slide, because it seems to me that to even state, to give the structure or state the axioms you would need in order to get a good analytic grasp on the basic objects, which are the simplicial types and some topos, you would need to have some rather strong extension of type theory, maybe modal type theory with not just crisp types, but also these modal operators of taking opposites and twisted arrows and maybe other reindexings along functors you have between the simplex category and various powers of the simplex category in itself. And then you might have enough structure. That's what I don't know. You might have enough structure to get an analytic grasp of these synthetic objects, so you can build them back up from discrete infinity groupoids. And then I think you could say that you have a foundational system. It's a little bit of a loose musing. I mean, I think the main use of this sort of thing is as a domain-specific language for reasoning about higher category theory, but I would love to hear some other opinions on this from participants, but that's how I see it.
So I see lots flying by in the chat that I'm not entirely following. If anyone wants to speak up, please go ahead. And Ulrik, I'll send you the chat after, so you don't have to worry about what you've missed.
Thanks.
Yeah, I can say something. So just on the issue of Grothendieck versus street vibrations, I think we're really always working with Grothendieck vibrations because we're lifting up to equality. It might not be up to strict equality, but up to equality. So it doesn't have the advantages that we usually have of Grothendieck vibrations because we still have to keep track of equalities between equalities, which is usually what we would have to do with the street vibration in the classical setup. Second, as Mike said, of course, if the base is univalent, there's no difference. But I think it's also, the definitions also make sense if the base is not univalent. And so it's a non-complete Siegel space. And then we would still be lifting up to equality, I think.
Yes, but as I said,
I don't agree that. I think that we should save the word Grothendieck vibration for the case when you have a displayed category or a type family, and then you can talk about lifting up to strict equality. And the other case, even though it looks like the definition of a Grothendieck vibration because it involves equality, should really be thought of as a street vibration.
Yeah, that's the point I try to make. I say by bringing in the flag structure, because I think that illuminates this issue you had in set theoretic definitions of categories, where you always have somehow an object flag of a set of objects. But if we bring that structure in, you can talk about, well, here's what's going on at the level of the categories, and if you want to look at some extra structure on the object flags, well, maybe you can do that. But I don't know to what extent you really want to do that and when you want to do that.
Other comments, questions?
No further question. So the answer seems to be yes. So the very basic theory can be done in a setting which is essentially street-like, because isomorphism is equal, because you assume isomorphism is equality. But then the question is, I mean, yeah, well, Ulrik, you said you did not try to prove bigger theorems using that, because I mean, using univalence is not an easy thing. I mean, as we all know, it's not necessarily making life easier. I mean, sometimes maybe it does.
Well, may I interrupt?
Because you have to prove the coherences and all those things. Yeah, so I mean, or maybe I should formulate it this way. How far have you got in doing ordinary theory of fibered categories in this more liberal setting?
Okay, I have not pushed that particular project. I think that's a great project that could be done in just basic hot at the level of one category theory, because the literature on fibered category theory is mostly about one category theory. Mm-hmm. So I don't know if I'll get around to this, but I think people should get around to formalizing that, and then that you can see whether it goes through. Here's my point that I would like to make, is that it's often easier to work with a univalent precategory, or where you forget about the object flag. It's just less things to worry about in this setting. From this point of view, that's the easy case, and you have more to worry about if you want to generalize to pre-categories or Siegel spaces.
I see, but I mean, yeah, I mean, I can imagine if you work with vibrations where they involve gadgets or categories, yeah, then one might expect to have the usual theory. Maybe it's becoming more laborious, but type theory allows you to sweep certain things under the carpet. But so I understand you that if you have no restrictions at all, so you essentially consider vibrations of genuinely of infinity categories. I mean, there the business is different. I mean, so
it rhymes.
So is it, according to your experience, a big difference whether you consider vibrations in your sense of yeah, general infinity categories or categories in the sense what would you say, precise terminology? I mean, these infinity categories which essentially correspond to categories.
Yes, of course, that's a big difference whether you work synthetically or analytically with categories. And in the type theory setup, we can only talk about, apart from two-level type theory, we can only talk about infinity one category theory synthetically. So that's what we have some experience with. Of course, for one category theory, we have an analytic definition in Buchholtz, which works very well. So somehow it's two different things at this moment. Once if we have an analytic definition of infinity one categories in Buchholtz, then we could do a comparison with the synthetic one and with what happens in one categories theory. Here's a question for you, Thomas. You have this sense that if we go through a book on fibered category theory, that'll be a results that'll be hard to do. Maybe you could post, maybe publicly to the hot list, a challenge of a particular result you think will give us trouble.
Well, I can even do it immediately. I mean, as far as I know, Jonathan is trying to do it. What I personally like a lot and is important in fibered categories with in view of doing categories of arbitrary base tuples is Moon's lemma, which essentially says that if you have a vibration of finite limit cats with stable and disjoint internal sums, that these guys are precisely correspond to gluings of finite limit preserving functors or pullback of fundamental vibration of the codomain of a finite limit preserving functor. This, I mean, is not enormously difficult, but it's a non-trivial, more advanced result in this way. If one can do this in this setting, I would find that very convincing.
One more thing I want to say just before, sorry, I'm interrupting someone. I do agree that it's very, very convenient in type theory to work with type families. I think Mike also said this. And of course, we find this when we work with formalizations. It's much better to work with displayed categories. It's much, but the point is that in homotopy type theory, you can always straighten and unstraighten and go back and forth between family and a map. So
that's cheap. I mean, because usually it's a heavy construction.
Yeah, it's fairly cheap.
I see. Yeah, that's of course fine because how should I say? I mean, the traditional approach, you morally all the time jump back and forth between fiber and an indexed view. But so why does one use fiber at all? Because it allows you to sweep under the carpet coherence issues in a very surprising way, which in general is not possible. When you do monoidal categories, you can't sweep coherence under the carpet. But if you work with fibered instead of index categories, so by sort of magic, all the coherence issues disappear. Yeah. Right.
Yeah, so maybe to reply to your previous question. So it is the case that Munz's theorem works in this setting, at least at the level of the corresponding types that you want to have. So these types should be some kind of maybe universe in a sense. So traditionally, there are also categories or two categories, which they are not, at least in this kind of type theory with these specific axioms, but you do get this typal equivalence. So you do get sort of the correspondence on the, on the level of
when using equality of objects as isomorphism.
Well, I mean, in this setting of notion of Cartesian fibration, which is in a way a bit agnostic to certain questions of strictness, I'd say. So for instance, in the paper, that's essentially just really the Riehl Shulman setup, where the shapes are taken as types as well. So we have some sort of equivalence between strict extension types and then the sort of book hot definable extension types. But that also means that, I mean, all of this vibrational theory can be strictified, and in fact, in the paper, that's also how we develop it, right? So we do work with fibers when we think about families, and the liftings really are strict, which we can express because they're formulated with respect to the extension types, the strict extension types.
No, but that would be nice to make precise, because as you said, and you said this to me before, that whether you have liftings up to isomorphism or up to equality doesn't make a difference. So there seems to be this a magic meta theorem, which I never saw spelled out, saying when you have a lifting up to isomorphism, you also have something up to equality, which essentially would mean that there is no difference whether you work with identity types or strict identity types in this particular case. Is that correct?
Yeah, so I mean, the point is that, I mean, this wasn't sort of part of the talk, but if you look at the original Riehl Shulman paper, it's true that in addition to the extension types, it's also good to postulate a certain principle, which can be called relative function extensionality. So it's kind of an extensionality, a function extensionality principle for terms of these extension types. And these basically guarantee a lot of good homotopical behavior. And I think this plays a role when proving this sort of strictification, destrictification results.
Okay. Interesting miracle.
Okay, any final questions or comments?
So it's still not very clear to me how you distinguish a DSL from a foundational system. I mean, probably this is not a very precise thing, but can you maybe say something more about this?
Oh, sure. So a foundational system is one where you do all of mathematics. And so any statement you translate into the system and you prove it. A DSL is a tool you might use for this purpose. So you might say, I want to prove something, and I use the DSL because it's convenient. And but then you need to have an interpretation or a model of it. And then in the foundational system, you would have to interpret that to get the theorem you're actually interested in if you wanted to use the DSL for some other larger development.
But according to that description, I think HTS or two-level type theory would be foundational systems.
Absolutely. The two-level type theory is a foundational system. It just somehow, it has a little extra baggage. Yeah.
Mm-hmm.
But so would I mean, the simplicial type theory extended with twisted arrows and whatnot would also have a lot of baggage. So I mean, I don't know, it's not clear which is the winner here. I mean, somehow this simplicial type theory would have everything be invariant, which is a a bonus. You can't make non-invariant statement, but I mean, I don't even know if it's possible to extend it to be a foundation system. I think of it mainly, as I also answered Dan's question, as a DSL, but to make use of it as a DSL in another foundation system, we again need to have a model theory of it, and we need to
Oh, looks like we've lost Ulrik. Ulrik, you're frozen. Okay. Well, why don't I stop the recording now, and maybe Ulrik will return. We can, at least in the recording, thank him again. He'll see that later, maybe. Okay, as I said, this was the last meeting of the semester. We'll meet again in September, and have a great summer or winter, depending where you are. Oops.